introduce Professor Raphael Bousso from UC Berkeley. Professor Bousso obtained his PhD from Cambridge in 1997. He is a student of Stephen Hawking. After that, he was a postdoctoral at Stanford, then Santa Barbara, and after a brief stint at Harvard, he became a faculty at UC Berkeley in 2003. Okay. He has given important contributions to string theory and quantum gravity. His paper on an explicit realization of the landscape is a classic, Bousso-Polchinski. More than that, he has a bound, the covariant entropy bound, named after him, and after naming an angle, this is the best that you can do in theoretical physics. So we are happy to have him here today. We will talk about black holes, quantum information, and unification.
Thanks very much for the kind introduction, Massimo, and thanks for having me back here. It's always a great pleasure to be at NYU. So, yeah, I want to tell you about developments from the last few years that I think are very exciting, where we're doing two things. We're understanding quantum gravity a little bit better, and we are also learning something about quantum field theory that we didn't know before. Now, in order to set the stage, I should probably justify my existence a little bit. Why would you study quantum gravity in the first place? This may not be what all of you do. So an obvious reason as a theoretical physicist, well, the history of theoretical physics is a history of unification, of describing more things with fewer ingredients. And clearly, general relativity and quantum mechanics or quantum field theory are the two pillars that we haven't yet been able to put under one roof. So you would expect that figuring out how to do that would be at least the biggest revolution as discovering quantum mechanics, say, or discovering general relativity. I mean, the hope is that we'll learn a lot about nature. But there are also specific questions for which we seem to need to understand how to put together gravity and quantum mechanics, like how the universe began, why it began the way it did, whether time is somehow special and singled out from the expected breakdown of space-time at singularities like the Big Bang or inside a black hole, or whether time itself is emergent, and if so, how. And so those are the kind of questions that ultimately we would hope to answer by figuring out how to put these theories together. And what happened in the last few years is that we've learned that quantum information is an incredible power. Quantum information theory is a very powerful tool for the pursuit of this goal. And so as I said, we're kind of making progress on two fronts. One is understanding how the degrees of freedom in nature that we see appear to organize themselves when we think of them as emerging from a quantum gravity theory. But secondly, we're learning that quantum field theory, non-gravitational theories, in other words, like the Standard Model, secretly know a lot about gravity in a way that I find really fascinating and that hints at that unification that we seek. Now, all of the recent developments that I mentioned have not only to do with quantum information, but ultimately came out of the study of black holes, and so I'll back up a little bit and review some of that. And again, I don't expect that all of you think about black holes all the time. So here's a lightning review. This is Karl Schwarzschild. He was the gentleman who wrote down the first exact solution of Einstein's equations that corresponded to, as he, I guess, thought of it, as the analog of a mass point or for localized mass, such as a star or a planet. What would the gravitational field look like outside of that object? I don't think he took his solution very literally as far as the existence of an event horizon and the interior of a black hole was concerned. This idea that maybe stars collapse and form such objects came later. This was right after Einstein came up with his theory. That idea was made very clear, I think, and how this works was made very clear by Oppenheimer. I think probably his greatest paper with Snyder, where they concerned themselves with this question of what happens when a sufficiently massive star collapses, and it's so big that it can't be stabilized by degeneracy pressure, it can't be a white dwarf or a neutron star. It's just going to continue collapsing. And in the fine tradition of spherical cows, he then solved this problem by just assuming that there's no pressure at all. And you take a cloud of dust, if you will, and you make it like a ball, spherically symmetric, constant energy density or mass density, and you just let it collapse. And it turns out that that's fairly simple to solve because you already have a solution for a dust-dominated universe, and you just cut out a piece. And then you glue that to a piece of the Schwarzschild solution because you have a theorem that allows you to do that, and it's still a good solution. And it was Oppenheimer who identified, I think, two of the key features that characterize what still puzzles us about black holes and what leads to problems such as the firewall paradox that I will not have time to talk about today. But I do want to stress these two features because they're made clear so beautifully already in the abstract of his paper, which is that if you sit on this ball of dust on the surface of it, or on the surface of a star, and while it's collapsing under its own gravity, nothing special happens when you cross this surface of no return, the event horizon. There's no sign there, there's no special events, it's very smooth. It's like you've walked one step too deep into quicksand, but there wasn't anything that told you that now you're not going to be able to run out of it anymore. And on the other hand, so this is sort of the infalling observer, there's nothing special at the horizon, and that also stays true later on when the black hole is sitting there. You jump in, general relativity tells you that by the equivalence principle, empty space at the horizon of a black hole is like empty space everywhere else, nothing special. On the other hand, if you're far away watching this process, it seems as if time sort of slows down. Oh, this was not supposed to happen. Okay, good. Time sort of slows down. I hope it comes back. Here we go. And the star just kind of freezes. In fact, back then I think they called it a frozen star. Wheeler later invented the word black hole for it. Good. So this leads to a lot of problems because these two descriptions really conflict with each other dramatically when you include quantum effects. And it seems like we can't both make the outside observer happy in terms of maintaining the unitarity of quantum mechanics and getting information to come back out of that black hole, and the infalling observer happy in terms of not having any special events and drama when they cross the horizon. And that tells us that either quantum mechanics or general relativity are wrong in a really severe way at the horizon of a black hole. So I've already said this, the black hole event horizon is the surface of no return. It's the thing that when you crossed, you'd have to move radially outwards faster than the speed of light to escape this collapsing region. So obviously you can't do that, so then you're trapped inside. And the classic example is the Schwarzschild solution. This is a sphere in that case with a radius proportional to the mass of the black hole. Now, let's consider the following question. What happens when I mess around with a black hole? For example, I throw some matter into it. Now you'd expect that it'll become a bigger black hole, I suppose, but exactly what happens? Or suppose I have two black holes, and recently LIGO has seen precisely this sort of thing multiple times, and they merge and form a bigger black hole. What happens to the horizon area of the black hole? It was, in fact, in the context of gravitational wave that Hawking published his famous area theorem to limit how much energy can come out of such a merger. There's an upper limit because he was able to show that the total event horizon area of all black holes in the universe cannot decrease in any classical process. Meaning, if you throw mass into a black hole, then the area of the event horizon goes up. This is not as obvious as it sounds because you can actually also throw the mass in such a way that you extract energy from the black hole. Nevertheless, even though energy comes out, no area gets lost. Okay, and then for this case of merging black holes, what his theorem guarantees is that the final black hole has area at least as big as the sum of the two participants in the merger. All right, so he proved this. Now, like all theorems, it has some assumptions going into it. And in this case, the key assumption is something called the null energy condition. The null energy condition basically tells you that you can't throw negative mass into a black hole. More precisely, it's the assumption that the energy density as measured by somebody approaching the speed of light, this k is really a light-like vector. So you're contracting the stress tensor twice with a light-like vector, that thing is never negative. Okay. Of all the various energy conditions that you may have heard about, weak, strong, blah, 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 this is the weakest of all the classical energy conditions. Nevertheless, it's wrong. You can write down quantum states in which it's just wrong, like Casimir energy is an example, but just one out of like infinitely many possibilities. So it's true for you and me and ordinary objects we study, but in general it's just not true. Okay, so let's just pause for a minute, forget about the area theorem, and talk about something apparently completely different. That just happened to be a question that happened to be asked around the same time, which is, so far we kind of discussed what happens to the mass of stuff when you throw it into a black hole, or you throw another black hole into the black hole. Now let's ask what happens to the entropy of stuff when you throw it into the black hole. This was something that John Wheeler made his student Jacob Bekenstein think about. And the thing that they were worried about is why can't you use that to destroy entropy and violate the second law of thermodynamics? So I've got my hot cup of tea or my ball of gas or whatever, and I just dump it into a black hole. Black holes seemed like they were very cold objects. They didn't emit any radiation. They didn't have any features. There's no entropy associated with them apparently. And so it looks like all this entropy is just gone. Now, what a lesser mind would have said is, well, it's not gone, it's inside the black hole, stupid. And so if you really worry so much about where your ball of gas and its entropy went, why don't you go jump into a black hole? And it turns out that that's not a good solution of the problem, because if you wait just a little bit of time before jumping after your ball of gas, you have no way of seeing it anymore. In some sense, it's already reached the singularity before you have any chance of receiving any signal from it inside the black hole. You can go check that. And so, the lesser mind might have said, well, okay, too bad, you should have jumped sooner. But still, I know it went into the black hole, so why are you worried about it? Well, I think what they were worried about is that the laws of physics should make sense to a distant observer. The laws of physics, if they're universal, should have an operational meaning. Like I should be able to go and check that the entropy of all the systems in the world has actually not decreased. Otherwise, what does it mean to claim this if you can't verify it? And so they cared about this a lot, and they ended up betting on the right horse by caring about this. So what Jacob Bekenstein came up with in 1972 is the idea that this is like when you put a hot cup of tea in the fridge. Its entropy goes down, but the fridge heats the room. There's another contribution to the entropy, in this case the air in the room, that you must not neglect, or you'll fool yourself into thinking the second law is violated. And in this case, the contribution had to come from the black holes themselves. Now he had to make a guess. What's the entropy of a black hole? There was no quantum theory that would tell him how many quantum states it has. You had to make a guess, and a good guess was inspired by the area theorem. Hey, area cannot go down. That kind of sounds like entropy can't go down. So why don't we just say the black hole has an entropy equal to its area. Now it has to be a dimensionless quantity, so you divide it by Newton's constant times h bar. I've set c, so the speed of light is 1 in all my transparencies, but I will keep these two constants of nature. And this product is indeed an area. It's the Planck length squared. Planck length is like 10 to the minus 33 centimeters. He couldn't fix this 1/4 with his guess, of course. That was fixed later by a calculation of Hawking's. Okay, so then this is the upshot. His proposal was, when you talk about the entropy budget in any process that involves black holes, you must not forget about the entropy of the black holes. And he called the sum of everything you already knew, the entropy of the stuff outside the black hole, plus the entropy of the black holes, the area of the horizon. He called that the generalized entropy. That's a terrible name. It's just the entropy, right? The same way when the fridge heats the room, you don't say, oh, the air of the room, now we have to include that. It's the generalized entropy. No, it's just the entropy. But I guess it was a weird enough idea that he felt he had to use a new name for it. And in hindsight, that's turned out quite useful. We use this name all the time. And that there's a theme in this colloquium, I guess, which is sort of encapsulated already in this formula, that we get to add together geometry and sort of an information theoretic quantity, and that's actually useful and tells us something about quantum gravity. So it's like almost too literal. Right? You get to literally just add them together. So what is the statement then? The statement is that thing, when you include all the terms in the entropy, so here they are again, that thing cannot decrease in any physical process. And this was actually only proven quite recently, at least in the semi-classical expansion, by Ehrenwall, who you see here. And I think it's really quite a major accomplishment. Good. So that's called the generalized second law. And again, it's just kind of the second law once you don't forget that black holes have entropy. Okay, well, Bekenstein was widely criticized for this proposal because it seemed like it was obviously wrong, because if black holes have an entropy, they surely have a mass or energy, so then they have to have a temperature, so they have to radiate. That's stupid because black holes can't radiate. Nothing comes out of them. That was actually something that was clearly articulated by Hawking. But then he did a different calculation involving quantum field theory in the Schwarzschild spacetime, and actually more general rotating black hole spacetime, and he discovered that, whoa, there's actually radiation arriving at infinity that has exactly the temperature that you would have expected from Bekenstein's proposal. And in fact, that's what fixes the 1/4 in this area formula. Okay. Now, that of course was a very important result, and I'm going to use only one little part of it here, which is that when a black hole radiates in this way, it loses mass, and so it's going to start shrinking. And indeed, the area goes down. How is this possible, given the area theorem? Well, the area theorem assumed famously this null energy condition, that the energy density of matter looks positive or zero to a light ray. This is violated near the horizon of a black hole, it turns out. And as I mentioned, it's also violated in many other quantum states that you can write down. Amazingly, Bekenstein's proposal, which had not taken this possibility into account, nevertheless handles it beautifully. What happens in this case is, it's kind of the opposite direction, right? Before you were worried about destroying entropy by throwing into a black hole some entropic object. Now the black hole is getting smaller and more entropy is appearing outside, namely the Hawking radiation. And so you do a calculation and you check and you find that that's more than enough to compensate for the loss of area. The exterior entropy increases by more than enough. This calculation was done by Don Page. Okay, so why am I telling you all this? I'm telling you this because it allows me, first of all, it's an important background story to this whole field, but also it allows me to give you a template for the newer results that I'm about to present to you in terms of something that might already be a little bit familiar. What I want you to think about is that the generalized second law is really a statement of unification. It's a statement about geometry and about quantum information, and you could have gotten that statement in two different ways. The way it was actually obtained is by worrying about the ordinary second law in the presence of black holes and fixing it up. By adding a term to it that's actually far from a correction term, like going back for a moment, here's the second law, which you would be violated if you only took account the entropy outside the black hole. Now you add to it a term, the area of the black hole in Planck units, typically that dwarfs the exterior entropy. It's much bigger. So it's not, the way that Bekenstein arrived at this, it wasn't like a correction, it was like a vast modification. But you could have also arrived at it by worrying about Hawking's area theorem in the presence of quantum corrections, such as black hole evaporation, or anytime you have some quantum state that you throw into a black hole that has some negative energy density. The point is, neither of these laws remains valid when you have both black holes and quantum corrections. But the GSL kind of unifies them both and appears to remain valid in those kinds of situations. So now I want to explore this a little bit further and imagine an alternate reality in which the GSL was actually discovered this way. There was no Bekenstein, nobody worried about the second law. Hawking discovered the area theorem, And then Hawking went straight on to discover that black holes evaporate. And so this is my alternative fact. In this case, I claim that Hawking could have discovered the second law of thermodynamics. I forgot to mention that in my alternative reality, people also did not know the second law yet. They were really obsessed with general relativity, and they forgot to discover thermodynamics. And here's how Hawking could have done this. Okay. So he's got his area theorem, then he discovers black holes evaporate. The area theorem doesn't work anymore, he's very upset. And now he tries to fix it up somehow. Same way that Bekenstein tried to fix up the ordinary second law, except in this case you can really think of the fix as a small quantum correction. He tries to find something, he realizes this is a quantum problem. It's a small quantum effect that's spoiling his area theorem. Maybe he can modify the statement of the theorem by including a correction proportional to h bar. Right? And because he's very smart, he eventually comes up with the von Neumann entropy of the fields outside the horizon. Oh, well, that's what I'm going to add. And then he would have not called this the generalized second law. He would have called it the quantum area theorem or something. Right? But it would have been the same thing. And it would have given him something that sort of reduces to the area theorem in the classical limit, but still works when quantum corrections are present. And then he would have stopped and thought, well, okay, but I'm into finding universal laws and stuff. I don't. So this new thing that I just found, it must tell me something even when there are no black holes present at all. Remember, here's the formula. He now say that this object here cannot decrease. Well, when there are no black holes at all, this area term isn't there. And you're left with the statement that the von Neumann entropy of the exterior fields doesn't ever decrease, which is kind of like the ordinary second law of thermodynamics. Now this is full of cheats that you don't get to ask me about, but that's kind of so. And, that's why I called it an alternative fact. But by the standards of today's alternative facts, I think it's fairly coherent. And so he could have literally discovered the second law of thermodynamics starting from gravity, from classical gravity. And so here's the scheme so we're going to try to repeat this game, okay, with some other statement from classical gravity. Here's the scheme we're going to try to follow. You start with a theorem in classical gravity that somehow involves the area. Then you do this replace area by generalized entropy thing, okay? This better be some kind of statement that would be violated when the null energy condition is violated. And then you can hope that by doing this, you can make it robust against violations of the null energy condition. And then you figure out how to take a limit where gravity becomes unimportant in some way, analogous to like not having any black holes in my example. And then you're left with a statement just about quantum mechanics. So let's see if we can do this with some other GR theorem. Well, I wouldn't be telling you about it if we couldn't. So the theorem we're going to start with is actually far more primitive than Hawking's area theorem. It's in every undergraduate textbook that discusses GR, the classical focusing theorem. And I'll remind you briefly what that is. And from that we get a quantum gravity conjecture called the quantum focusing conjecture. And then we figured out a way to get rid of the gravity part of it and discover something, in this case, genuinely new that was not known about quantum field theory, and which we were then able to laboriously prove. But it's really easy to get it this way. So the first step in doing this is we have to liberate this concept of generalized entropy that Bekenstein invented for the black hole horizon from the horizon. Okay? It turns out that really everything that goes into this idea is the area of a surface and the entropy on one side of it. There's no reason why that surface has to be on the horizon of a black hole to make sense of the notion of generalized entropy. Now, there's maybe no particular reason why you think it would be useful. It turns out to be really useful to think about generalized entropy for arbitrary surfaces. And this is something that I learned from Aaron Wall, who really pushed this idea in a very smart way and got lots of beautiful results that I don't have time to review here. But here's a picture that you're going to see over and over. So this fat black line here is supposed to be all of space at one time, or we call it a Cauchy surface in general relativity. And this dot represents a two-dimensional surface. So I'm suppressing a lot of dimensions here. That divides space into two sides, which you might call inside and outside and so on. Right? So it could be like a spherical surface, but it doesn't have to be. No symmetries are assumed here. Now in my pictures, light, so time goes up. If I include time at all, it goes up. And in that case, light will go at 45 degrees. So this green line is really a bunch of light rays that are coming out orthogonally from my surface and moving forward in time. And these would be light rays going out in the opposite orthogonal direction. And these would be light rays going into the past or arriving from the past. Okay. So one thing I can do is I can consider the generalized entropy of such an arbitrary surface. Let me first review the classical statement. Yeah. So the focusing theorem is a statement about something called the expansion of the light rays, which is exactly what you would think it is. Namely, if you have a surface, let's say in flat spacetime, in Minkowski spacetime, and it's a sphere, let's say, a sphere at an instant of time. Now you look at light rays coming out of that surface, like let's say laser guns fire on the outside of that sphere. The path they take through spacetime, well, they move away from each other, right? Each of these light rays are expanding away from each other. That corresponds to positive expansion. If you had the laser guns on the inside and they fire towards the center of the sphere, well, they would be contracting. That'd be negative expansion. Mathematically, it's a thing that's locally defined. So if you have a light ray coming out from the surface, you just look at the neighboring light rays and see if they're getting closer or moving away further. The logarithmic derivative of a little area element like that is what the expansion is. Okay. But it's really kind of an intuitive concept, I think. And I think this is still intuitive. The classical focusing theorem is just a very simple statement that matter, classical matter, if it satisfies the Null energy condition, such matter focuses light. And we use this in astronomy all the time to get lots of information about the universe, weak lensing and so on, right? But it's the statement like if I've got parallel light rays, let's say, coming out of this wall, so then in that case they start out with theta equals 0, what's the derivative of theta? Well, if they go through matter like you and me, they're going to get focused. They're going to start moving towards each other, like bending of the light by the sun and so on. These are familiar things. They will not do this, where they start out parallel and suddenly start to diverge. They can only do that if you violate the null energy condition, if you have negative energy density around. Okay. And so, of course, we are concerned here precisely with such violations. This kind of anti-focusing is precisely what happens, for example, when a black hole evaporates. You've got light rays hovering near the horizon. Suddenly they break free and start spanning larger and larger spheres and get out to infinity. And so our idea was to just see if we can fix up that theorem by adding a quantum correction to it and then seeing where that leads us. So this is work with my former student Fisher, who's now at Perimeter Institute, postdoc Leichenauer, and another postdoc, Aaron Wall, who I already mentioned. What we did, well, the first thing you need to do is define a quantum version of what you mean by expansion. Now, the idea, of course, is that the classical expansion is defined in terms of the variation of area as you move up or down a light ray. And so we're going to define the quantum expansion by considering the variation of the generalized entropy. It's a bit of a more non-local quantity because what the generalized entropy does actually depends on what your surface is doing away from the place where you're deforming it, where you're following a light ray. But okay, so we can handle that. So we fix a surface and we deform it, but you can't see this in this picture very well. We deform it only along one light ray. So I don't know if I can draw this real quick, but so let's say this is our original surface and here's a bunch of light rays coming out of it. Right, and we pick one of these light rays and we deform the surface like so. And we can ask, how does the generalized entropy change? So generalized entropy, let's say, is the area of the original surface plus the entropy out here. And we compare that to the area of of the deformed surface plus whatever the exterior entropy is now that we have perhaps, moved some of the matter that was here is now inside the surface, so the exterior entropy is not the same as it was before either. So both of those things now change, and we can take the derivative, the rate of change, as I move along one such geodesic. It's really a functional derivative if you want to be precise about it. Okay, here's maybe a better picture where you have suppressed only one spatial direction. So this is the initial surface. This is a bunch of light rays orthogonal to it, this green stuff, and the yellow stuff is supposed to be the part of space outside of that surface. And now I'm going to consider, as a function of this deformation parameter, I'm moving the surface a little bit along one light ray. How does the exterior entropy change, and how does the area change? So that defines a kind of derivative. That's the quantum expansion. So we give that the name capital theta, and expanding it back out into its constituents, it's the classical expansion plus some kind of derivative of the exterior entropy. You have to have, there's really, this change in the exterior entropy is proportional to how wide you make the cross-section of your deformation. So in the end, you want to take the limit where you take that cross-section to 0, and then it turns out that this combination remains finite. Okay, so this was actually the only hard part of this. Once we've defined what we mean by quantum expansion, it's fairly obvious how we're going to guess a quantum version of the classical focusing theorem. Here's again the classical focusing theorem. It does rely on the null energy condition. Well, we just replace classical theta with quantum theta. So let's make it a capital theta, and that's the conjecture. That's the quantum focusing conjecture. So again, it's actually quite simple. I mean, there's not much that goes into it, other than these definitions. But it's very powerful. So the statement that the quantum expansion will not decrease in any semi-classical setting, even if the null energy condition is violated, has many interesting consequences. Okay, one of them is obviously the classical focusing theorem in the classical limit. It reduces back to that. Another, which I also won't talk much about, is that you can get Bekenstein's generalized second law as a special case, and then of course again in the classical limit Hawking's area theorem. So it implies all of those things. I'll talk a little bit about items 3 and 4. This is perhaps more for people who might have heard of these concepts, and I won't go into detail. I really want to save my time for item 5, the quantum null energy condition, which is the part where we throw away gravity and we get a new result in quantum field theory. That's why I think it's worth spending the most time on this. So the covariant entropy bound is a statement that basically sort of encapsulates this idea that the world is a hologram, that the number of degrees of freedom is somehow controlled by the area of surfaces and not as you might naively expect, or even not so naively. You think it scales like the volume because you have quantum field theory and it's local, and so you can excite degrees of freedom in different places. Well, it turns out in the presence of gravity, that's not the case. So here's a statement of the covariant entropy bound, and this is something that was, well, so I formulated this bound in like 18 years ago, and it was just kind of a guess. And we can now get it in like a couple of steps from the quantum focusing conjecture, and actually in a better formulation than the one that I gave back then. It's a more precise formulation where you say exactly what you mean by the entropy. So here's how this works. So here's a surface we're going to start from. This is, a two-dimensional spatial surface. And let's say this is what we call the exterior region. By the way, it doesn't matter which side of the surface you call the exterior, as long as you then stick to that. So let's pick this side. And here are a bunch of light rays coming out of the surface. And in this, I'm going to assume that these light rays are initially not quantum expanding. Okay, the initial quantum expansion is not positive. Okay, well then the quantum focusing conjecture tells you that it's not going to become positive because theta prime is negative or 0. So the quantum expansion can't get any bigger. It's negative to start with. Okay, so then integrating one more time, that guarantees that the generalized entropy of the later surface sigma prime is less than the generalized entropy of the surface sigma. It's pretty simple. But now we can unpack this, at least in those cases where matter is well localized to this light sheet n and crosses it in a way that's sort of well localized between sigma and sigma prime. In that case, you know what you mean by these two areas and by the entropy on those two slices separately. You don't have to think of them in combination. In general, that's actually not true. The generalized entropy is better defined than each of the things that go into it separately. This is a divergence that's really canceled by the RG flow of Newton's constant. And so in general situations, you have to consider this object as one thing. But in many practical situations, like a ball of dust crossing this light sheet, you know what you mean by the entropy of a ball of dust. You know what you mean by these areas. You use the infrared Newton's constant. And so you can unpack this. And this is actually the statement of the covariant entropy bound. This says that the entropy that crosses a light sheet is always less, actually more strongly, it's not just less than the initial area, but it's less than the difference between the initial and the final area. Okay, so you just recover that from this theorem, which in turn is just the dumbest thing you could have done to the classical focusing theorem. And out comes this bound, which at the time I thought was actually kind of cool. But yeah.
Maybe that was completely misunderstood. It seems to me that I could invent a very, very massive ring.
A very
massive ring.
Ah.
And if I'm able to do all of this in some localized thing, which it seems like you're saying I could, I have a light beam that's starting off parallel, but the beam makes it spread.
Yeah, it can't do that. That's what's guaranteed by the classical focusing theorem. That's just not, it will not work. And you can, I mean, that's what these theorems are good for, right? Because otherwise you could dream up all sorts of complicated examples, but this way you just know from the start it's not going to work. And the theorem follows this directly from Einstein's equations. I mean, if you can always follow this through in detail in any particular example. I mean, the ring will have to collapse or it'll form a horizon around it because you made it too massive.
So that's the sort of story.
But that's, yeah. But after you've done a few examples like this, of course, you tell yourself, well, wait, why does this never work? Well, that's why it never works. It's because there's a theorem that says it can't work. Good. So there's one more topic that I wanted to treat briefly. Which is that there's actually something called holographic screens, which naturally arises out of this notion of the covariant entropy bound. After all, the bound was sort of an attempt to make sense of the idea that was at the time advocated by people like 't Hooft and Susskind, that the world is kind of like a hologram. You can store all of the information on two-dimensional surfaces at a density of no more than 1 bit per Planck area. And yet there were obvious counterexamples to that statement when you think of the information as living on a spatial volume and the area as being the boundary of that volume. The dumbest counterexample is if your space is a 3-sphere, and you take a tiny little 2-sphere that encloses an enormous volume on that 3-sphere, nearly the entire thing, then clearly you can violate these kind of things. But by considering light waves that come out of the surface, that sort of rescues the idea. And so now you can ask, well, does that really mean that I can always find suitable surfaces in a space-time on which I could store all the information at a density of no more than about 1 bit per Planck area? And the answer is, yes, you can do that even if the space-time doesn't have a boundary. You can do that even in a closed universe, for example. And here's how you would do it. So this is a Penrose diagram, light waves at 45 degrees, but things are a bit distorted in terms of distance. So this is actually infinitely far away. This is the Big Bang. And let's say this is U. The green line here is your past light cone today. That's your past light cone tomorrow, day after tomorrow, and so on. And clearly, your past light cone has 0 area at its tip, and then it's going to have 0 area again when it hits the Big Bang down there, because all distances are 0. And so there's a maximum area somewhere along the way. And that's a special kind of surface on which the covariant bound becomes particularly powerful, because remember, we had this non-expansion condition for it. So you're required that the expansion away from the surface is not initially positive. Only then are you allowed to claim that the entropy on the light sheet is less than the area of the surface. But for these maximal area surfaces, that means because they're maximal, you get to go both in this direction, but also in that direction. And so you get to bound the entropy on an entire slice of this null foliation in terms of the areas of these surfaces. So slice by slice, the claim would then be that you can store all of the quantum information on these spheres. I mean, you shouldn't take that too literally. It's not like if you look there, there's all this information. But in terms of like counting how much information there is on every slice, there's no more information, no more possible different quantum states, let's say, than e to this area of this and this and this and this. Okay. So the connection of all these dots, it's like a two-sphere cross time or something in this case, is called a holographic screen. And only quite recent, there's a similar thing when you collapse matter to form a black hole. Here you have what's called a past holographic screen. Here is a future holographic screen. Only recently, together with Netta Engelhardt, we were able to show that these holographic screens satisfy an area theorem. And that's quite useful because as important as Hawking's area theorem was, it only applies to the area of event horizons. And most spacetimes don't even let you define what you mean by an event horizon, let alone have any. In particular, it's not clear what you would mean by the area theorem and therefore, going to the quantum case, the second law in cosmology, like the universe we live in. Well, here's an area theorem for the universe we live in. The past holographic screen cannot decrease in area. It's monotonic. Similarly for future holographic screens, except it goes in the other direction. Okay. So proving this was quite non-trivial, but and of course, we again, for a classical theorem, as usual, we needed the null energy condition. This is Netta. She is currently postdoc at Princeton. Now, since we needed the null energy condition, it was very natural to try to generalize this in exactly the same way that Hawking's area theorem sort of lifts to Bekenstein's generalized second law. When you include quantum corrections, you're starting to get the idea. Well, in this case, it's a little more subtle. You first have to define the quantum corrected screen. So instead of maximizing the area along your, on your past light cone, for every cut, you look at the entropy outside. Oh, still getting bigger. The sum of the two, still getting bigger. Oh, now it's getting smaller. So you find the maximum generalized entropy, okay, which is not exactly going to be in the same place. But then the claim is that the generalized entropy, after you've done that for each one of these light cones, when you then look how it evolves along these maximal slices, the claim is that it always increases. Now, that's a conjecture, and I don't have a proof for it. But what I can tell you is that if for some reason you believe the quantum focusing conjecture, it follows from that one. So what I'm trying to develop here is the notion that quantum focusing conjecture is very strong logically. A lot of things that we either know are true or have a lot of evidence are true follow from it. It's a very unifying statement. Okay, so now I want to sort of loop back to our original storyline. Remember, the storyline was we want to play this game where we start with a GR theorem, lift it up to some quantum gravity statement, and then get rid of the gravity heritage, or at least hide it somewhere under the carpet, so as to obtain a hopefully novel and interesting statement about quantum theory or quantum field theory. So so I'm reconnecting with that now. We're not going to exactly throw away the gravity part. I'll tell you precisely what we're going to do. So here's again the expansion, the quantum expansion unpacked into its constituents, the classical expansion and a kind of derivative of the exterior entropy as you vary some surface along some light ray. Okay. And remember, the quantum focusing conjecture is that big theta prime is non-positive. Okay. Now, to get something out where you learn something about quantum mechanics and it's not all dominated by the geometric term, by the general relativity term, you have to face the following issue, right? This thing has an h bar in it, gh bar. This is a purely geometric quantity. So for example, if you have a sphere of radius r in flat space-time and you ask what is the classical expansion theta of light rays orthogonal to that sphere, it's either plus or minus 2 over r, depending on whether the light rays go towards the interior or the exterior. So in the limit that we're working in here, which is an expansion in GH bar, this term would be vastly subleading to that term, and it would just not be very important. Okay. Now, what we're going to try to do is make this term equally unimportant, and they're both important. Okay. Now, how can you do this? Well, you could start by trying to make little theta, the classical expansion, just 0. So, for example, if you have a plane in flat spacetime and you send light rays out orthogonally to that plane, they're exactly parallel to each other, and little theta will be 0. Oh, great. So now we've completely gotten rid of what would normally be the dominant term. Well, not completely. Because as those light rays pass through, say, this room, you guys are going to focus them a little bit. And the strength of that focusing, though, is proportional to G Newton. Just like bending of the light by the sun, right? It's proportional to G Newton. So at linear order, what this accomplishes is to make the first term in the expansion also proportional to G Newton, just like the second term. So we haven't really gotten rid of it completely, but we've gotten to a point where we've got G Newton appearing in both of them. And so when we now say that theta prime is less than or equal to 0, the G Newtons can just be cancelled out. And they're gone. And so it seems like we've gotten rid of gravity. But of course we used gravity in order to figure out how this classical theta behaves. Gravity is what makes those light rays pick up some expansion. But again, we've accomplished making them both of the same order in G Newton. Now, of course, there are nonlinear effects in the bending of these light rays. And you know, there's terms quadratic and cubic and so on in G Newton, which normally would be, would give corrections. But let's suppose that we now take the limit as G Newton goes to 0, right? Well, because we can divide the entire equation by G Newton, and these two terms don't have any G Newton, and then there's a bunch of terms here which have G Newton remaining. Well, now I can just take G Newton all the way to 0, and only the first two terms will survive. And then I only have H bar in the final statement. So let's see how that works in detail. Okay, you don't have to follow all of this, but what I want to emphasize is, though it looks a tiny bit busy, this is the entire derivation of what we will call the quantum null energy condition. And I'll contrast that in a moment with how hard it is to prove this condition in quantum field theory. Of course, we're deriving it here from a quantum gravity conjecture, and so this doesn't tell us that it's necessarily true. But the fact that we can get it so easily from this conjecture, and that it's so hard to prove it in quantum field theory, I think is interesting. It tells us that there are some aspects of quantum field theory which are most naturally understood from the point of view that gravity is actually present in the real world. Quantum field theory knows secretly about the existence of gravity. So here goes. So this little part over here is just, again, the quantum focusing conjecture, theta prime less than 0. Then we unpack theta prime into the classical little theta prime, and, well, something that's now kind of like a second derivative of the exterior entropy. And the classical theta prime, well, there's an equation for that. It's called the Raychaudhuri equation that basically tells you that matter induces focusing. So here's some stress tensor that's going to make the expansion negative if it starts out 0. And then, if you already had some non-zero expansion, or what's called shear, light rays kind of moving apart in one direction together in others, well, they all contribute to this. Okay. And here's the quantum part again. Now, we said we had to be clever to sort of isolate a purely quantum mechanical equation, or quantum field theory equation. We were going to choose a surface whose initial expansion and shear would be 0, and we can do that. And in that case, all the black terms are 0, and only the red terms survive. And ordering them in this way, we find that the stress tensor is greater than or equal to a second derivative of the exterior entropy, and again, you should think of this derivative in terms of a functional derivative really, but think of a small deformation and it's a derivative with respect to this deformation parameter. The stress tensor is bounded from below by kind of the second derivative of the information that's coming in across the surface. So that's the quantum null energy condition for obvious reasons, right? The classical null energy condition would just have a 0 here. That was the definition of it. And so we're now replacing that with this statement, and hoping that now it'll be true even if the null energy condition is violated. So again, I think it's remarkable that we can get a statement like this starting from pretty much the stupidest theorem in the GR textbook. Because it's not like people weren't trying to find lower bounds on the stress tensor. And it's known that there is no local lower bound in the stress tensor. So what people did instead is come up with ideas like, let's integrate the stress tensor over an infinite light ray. And then maybe that always has to be positive. That's called the average null energy condition. But this is really a lower bound on the local stress tensor. Of course, what we're doing instead is the lower bound itself is a non-local quantity. Right? The exterior entropy and its derivatives are, well, they depend on what this surface is doing elsewhere. They depend on, for example, as I deform this surface, let's say I hit some electron here that's now no longer outside, no longer contributing to S out prime. But exactly how that changes S out prime depends on whether that electron is entangled with and purified by some other electron in some EPR pair, say, and whether the other electron is inside or outside that surface. So it depends on stuff that's really far away. So now the right-hand side is kind of non-local. And the way that I would intuitively think about this bound is, again, if I was receiving information through some signal that somebody's sending me, perhaps in photons or something else that's moving at the speed of light, what this is telling me is that the rate at which I am receiving information, if I analyze this signal optimally, would decrease necessarily if the signal contains a patch with negative energy density. And if I want the rate at which I'm receiving information to increase, I want my friend to send me positive energy density, otherwise it can't be accomplished. And so I want to emphasize, this is all stuff that you could in principle, measure in the lab. But most importantly, for the remaining few minutes of this talk, we can try to prove this statement. Because now we're not in the unknown realm of quantum gravity anymore. There's no G Newton here, only H bar. So we should know whether this is true or not. And so we did manage to prove it for free fields. And this is a couple of pages out of our paper trying to prove this for free fields, just free quantum fields. And it goes on and on like this. And so my point here is just that, again, this is a property which is quite hidden in quantum field theory. So maybe this is why people hadn't discovered it previously, even though it seems like the statement itself is very simple. Stress tensor is greater than second derivative of entropy. So given the time, I probably will not go over the details of how this proof is done. But this was the same group of people plus another student, Jason Culler. But again, this was just for free theories. And then Culler, together with, again, Stefan Leichenauer, who played a big role in these developments, managed to extend this to a particular class of interacting theories. So assuming the ADS-CFT correspondence, there are if you have a quantum field theory which has a conformal fixed point that has a gravity dual, then you can use the ADS-CFT correspondence to compute stuff like the entropy and how it varies, which otherwise is extremely difficult to get a handle on. And so using that, they were able to show that the quantum null energy condition also holds for interacting theories with the gravity dual. So at that point, of course, you're starting to think that this might really work. And this proof in turn inspired okay, you can also worry about higher curvature corrections. There are counterexamples, but they're actually beautifully resolved by the fact that you need to have your effective field theory valid when you do the deformation. You can extend it to curved space. This was all done by a bunch of students of mine together with Stefan Leichenauer, and also Don Merrill's group at Santa Barbara, working with one of my students and one of his students. And so, okay, so this all worked out beautifully. But then the thing that really stunned me was that Tom Faulkner and his group at the University of Illinois was able to give the sort of fill the remaining pretty huge gap of all interacting theories. You didn't just want this to be true for free theories and theories with a holographic dual. You wanted it to be true for all quantum field theories with a conformal fixed point, and this is the proof. And this paper is like 77 pages, and it's really it's the kitchen sink. I mean, he uses everything we had, or he knew, I didn't. And he proves this statement with his collaborators. So this is Tom Faulkner, and obviously it's a very technical piece of work, but it exploits very recent techniques that were applied to proofs of this average null energy condition that I mentioned earlier. There were actually two different proofs for that, and that was kind of weird. One relied mainly on quantum information theory and the monotonicity of certain so-called full modular Hamiltonians, never mind. And then another proof that relied on causality and the way that operators are moved within certain causal regions by the application of these modular Hamiltonians. That's called modular flow. And so there were these two ways of proving the average null energy condition. And now we kind of know why there were two ways, because it's really when you want to prove the quantum null energy condition, which implies the ANEC as a special case, then you need them both. And so he combined them in quite a non-trivial way and was able to show this. And so this is really just a statement about quantum field theory, which is now established. And again, I find it fascinating that it was so easy to get this by thinking about gravity and semi-classical quantum gravity, and so hard to verify and prove it in field theory. And so I want to close with that. I should mention that there's ongoing work. There's some speculation that the QNEC might actually be saturated in all states. So there's ongoing work again by Stefan and some of my students that was based on these holographic kind of calculations. So that would, if it succeeds, establish saturation only for such theories. But it got Tom Faulkner interested, so he also had some ideas about how to prove it more generally with his collaborator and another one of my students. Here are some of these people. This is Stefan. These are my students working on this, and that's Tom again. And so this is still sort of happening, and we'll see where it ends, but I hope that you found it interesting, so thank you. Probably, but it feels like it's still a bit of a haze to me. I mean, so there are recent proofs of the A theorem that use very similar techniques to the proofs that have gone into this. So it feels like there should be a relation. I don't think that has been elucidated very clearly, and it's probably worth trying to do that.
Yeah, to see if they contain the same, if they overlap, the same.
Yeah. Yeah.
Yes. Are there a lab system which would come close to this?
Well, as I sort of hinted here in the last slide, though I find this extremely surprising, but we can't exclude that all states saturate this bound, and that the stress tensor is really nothing but the second derivative of quantum information. In that case, all lab states would saturate it too. But it's well, Yeah, because you can, you can measure these things in principle. I mean, of course, measuring a von Neumann entropy directly is tricky, but you can in principle do it if you replicate your system many times. Because you can define the von Neumann entropy as a certain limit of Renyi entropies, which can be directly measured as the expectation values of linear operators on multiple copies of a system. So you do have the option of measuring it. It's a pain, but you can do it. Now, at least at the level of what we've already established, of course, if you showed that the quantum null energy condition is violated, what that would then show is that quantum field theory is violated. So that would be very surprising. But yes, the quantities that are on both sides of the equation are perfectly well defined, and you can measure them in the lab.
So I have a very basic question. I think about thermodynamics as some set of statements valid in some thermodynamic unit, whereas in this gravitational treatment, in principle, I don't see any thermodynamic unit present.
Well, I wasn't. Yeah, so I wasn't really using most of what goes into thermodynamics. I was using the von Neumann entropy of quantum states. And that is a perfectly well-defined object, whether or not you're in some thermodynamic limit, right? So literally what the von Neumann entropy is, and I should have maybe spelled it out a little bit more clearly, is, so if you have some region of space, let's say you start with all of space, your quantum fields have some quantum state, which we might call rho global. So I'm describing it as a density matrix just to be general. It doesn't have to be a pure state. And then when you restrict that state to one side of some surface like this, let's say the outside, right, you can define a density operator rho out, which is just the trace over the interior degrees of freedom of this global density matrix. So that's like a reduced density operator. Right? And given such a density operator, you can define the von Neumann entropy as in the usual way. Right? So all of these things have nothing to do with thermodynamics. They're just defined in any quantum state.
But the statements about the evolution of these objects are independent of any thermodynamic unit?
Yeah.
I actually want to continue this same question. The statement that this entropy increases in time, to prove this statement requires some assumptions. You have to assume something. You cannot prove it without anything.
Yeah. So it's
the role of such assumption.
It's surprisingly well. Of course, there are assumptions, but they're surprisingly weak. So all that we really needed was a unitary Lorentz invariant quantum field theory. But those two things are important. So this would not be the case in a non-relativistic quantum field theory. It would not be the case in a non-unitary theory. So there are things you could imagine to which this would not apply.
I suppose that another way of asking your question is in classical mechanics to prove the H theorem, you need to make assumptions, and actually it's not fully proven here because you would need answers, etc. So here it seems that
because you don't solve that problem, right? When you consider the generalized entropy, there is an asymmetry in the definition of it. Namely, the area term. I don't know if you can see this well if I write it up here. So the generalized entropy is this sum, right, of area plus the exterior entropy. This is a sort of microscopic entropy, not coarse-grained, which I'm just defining as trace rho log rho. So if, for example, if all I had was this, and there was no area term, just consider this maybe in all of space, then the second law or any of these statements would be trivially satisfied because this just doesn't change at all by unitarity. right? This thing, on the other hand, we should probably think of as a coarse-grained entropy, where we're lumping together all the quantum states associated with having such an area around in your space-time without knowing precisely which one it's in, which is why all of that contributes to the entropy. And it's the interplay of these two things which gives rise to a lot of non-trivial and interesting questions and statements like this. But they do not in themselves contain something like the H-theorem, where you would have to ask about the coarse graining of the ordinary matter fields. And so that's why you're not seeing any of the assumptions or kind of finer points that go into that theorem in this analysis.
So if you understand correctly that this coarse graining happens in Hawking's area theory somehow, and then in your construction, regular entropy gets infected by these from area.
I think that's a good way of putting it. Yeah, I like that. I mean, right. So what's happening, let's go back to the original example of the generalized second law for black holes, right? Presumably, if the world is unitary and black holes return information and so on, if you throw a cup of tea into a black hole, the phenomenon entropy of the somehow quantum gravity state for the whole universe should not change because everything is unitary, right? But if I coarse grain over the black hole part and take care of it by just counting the area of the horizon, then there's an opportunity for the entropy to go up, even if I keep the fine-grained entropy on the outside.
I have a couple of questions. First, you just mentioned you use Lorentz invariance to prove this result. So does it mean that it won't apply in a quantum field theory across space-time?
No, it's local Lorentz invariance. Yeah.
My other question is that naively I would expect that the entropy in the outer region in a quantum field theory would diverge because of
Yes.
your medium.
Yeah, that's a very good point. So this is why I alluded to this briefly when I said that this sum is better defined than either of these pieces separately. And it's really a sum that contains a bunch of other terms. So this exterior entropy outside of some surface actually contains an infinite contribution that's proportional to the area divided by some cutoff that has to do with the fact that quantum modes that are localized to one side and to the other side of the surface are actually entangled with each other and purify each other. So if you cut through the middle, you get a huge... So this you get even in the vacuum. And there's a very large body of work. So, and on the other hand, Newton's constant here also depends on the scale. It also suffers from an RG flow. And so there's a significant body of work starting with Susskind and Uglum, and there's lots of papers by Solodukin and so on, where people sort of investigate what happens to these two terms, and actually also to subleading divergences in S out, which turn out to be... So you can think of this like a counter term to this area divergence. There's subleading divergences. There are counter terms in things called the Wald and Dong entropies, which I neglected to include, which cancel those divergences. And it's really the sum of the two that makes for a good quantity that has, yeah.
But however, I was thinking about the inequality, where you have the true derivative of the entropy divided by the area.
When you have the, sorry?
The ratio of
Good, yes. Yeah, so then once you start taking derivatives, there's an opportunity for these divergences to drop out much more easily, right? Right, because they're the same. So for the kind of surfaces that we're considering in the first place, this sort of null plane, it doesn't matter how you cut them, these divergences are always the same. And so they drop out.
Okay, so maybe we have time for one last question. Maybe I can ask one last question. You proved these theorems at some point using Einstein's equations. So that means Einstein's equations enter in proving at least not the flat space theorem.
Well, sorry, we did not prove them using Einstein's equations. We got the conjecture using Einstein's equations. But then, a quantum null energy condition doesn't have H bar in it, and we prove it just in quantum field theory.
But is there a way in which you can reverse the flow and try to use, to arrive at Einstein's equations using some properties of the generalized entropy?
Yes, so, right, there's maybe. I mean, there's a set of ideas. So, right, so the idea would be that, in an arbitrary space-time, locally you can always put a little sort of almost flat cut like this, and then maybe try to exploit that to work backwards. This is kind of similar to some ideas that Jacobson had way back to try to use black hole thermodynamics to kind of recover the Einstein equations. I don't know how rigorous one can make these ideas, and I don't think it's been explored in any depth.
Thank you very much. We can continue discussion on the 10th floor of our new building, 726 Berkeley.
Thank you.